And here's the function. Number 1, f of x equals sine x minus x squared plus 2. Because this is the same with sine x minus x squared plus 2 equals 0. So this is our function. Sine x minus x squared plus 2. In step number 2, I will say that f of x is continuous everywhere as a difference or sum of continuous functions. In step number 3, I will plug this function in the calculator in y equals, and I have sine x. Make sure that the mode is in radian mode. Your calculator is in radian mode. So sine x, close the parenthesis, minus x squared, and then plus 2. I can graph and just have an idea, or just plug in some numbers, go to second and table. And it happens that I already have a solution. It's between 1 and 2. At 1 is positive, at 2 is negative. That's good enough. So 1 comma 2, f of 1 is greater than 0, and f of 2 is less than 0. From 1 and 2, these two, by the intermediate value theorem, there exists a C and we are calling it R now, it doesn't matter, between 1 and 2, such that f of C is 0. In step number 4, I'm going to say I pick x0 to be, and we'll decide in a minute. In step number 5, I find f prime as cosine x minus 2x. And I realize that with 1 or 2 it doesn't matter, the derivative will not be 0. I'll start at 1. I have to decide, I didn't read the entire problem, how many decimal digits. I'm going to say 6. Accuracy. And now I start in 7, if you want, I start Newton's method, which has to be x minus f of x and everything divided by f prime of x. This is what I plug in the calculator. Don't erase the function. We are going to use it. So I don't have to type it in again, but I have to insert an x and minus. So x minus and parenthesis for the numerator. Go all the way till the end. Close the parenthesis and divide by another parenthesis, which is cosine x. Close the parenthesis for cosine and minus 2x. Tell me whether you're okay with this, or you want me to show it again, or is it blurry? I'm not sure. Can you see?
I'm able to see what you have in there.
Okay. Any questions?
No.
Okay. So now, second and quit, and just go to variables, and go to y variables, and select the function. And I am going to select function y1 because that's where Newton's method is. And I'm going to put parentheses and I'm going to plug in this number. That was our choice, my choice of x0. Press enter. And this is our first iteration. So x0 was 1 and x1 is 2.26154271. And you can say, oops, what do you mean by this? We are looking for a solution between 1 and 2. Look at this number. And I'll say, yes, it's possible that it jumps the first step. So now let's go to second and copy the entry, but please overwrite 1 by second and answer. Because now I want the calculator to plug in this x1 everywhere and give me x2. I'm hoping now that x2 is between 1 and 2. And it gets closer. So x2 is 1.807334422. And now I don't have to do anything else, just repeat. x3, 1.73087246. I continue. x4, 1.728468707. And most probably I have enough. I have 2, 4, nope. I'm right here at the 6th digit. 1.728466319. The next one is guaranteed to be identical. So there is no need for that one, and I will say this is the answer to the accuracy, with the accuracy that I wanted. 6 decimal digits.
So you're picking that sequence of numbers because it's no longer repeating.
Yes.
6 numbers.
So when it stops, yes, when they start repeating, I stop and I say, that's it, that's all I want. Yep.
And then for x0, you determine that because of the
intermediate value theorem gives me those numbers, and I can start at 1 or I can start at 2. It doesn't matter.
Okay.
Just make sure that f prime is not 0 at the starting point, because otherwise it will be here and you will not be able to pass the first step. It will give you an error from the beginning. Is that clear?
Yes, it is. Thank you.
Okay, very good. Do we understand Newton's method? This is all based on what we've studied in this class, obviously. So what would we like us to do next?
Could we see one more example of it?
Yes, of course. Would you like to choose?
You always seem to pick the best ones, and I trust your judgment.
That is not really true. I say that about you. Okay, so we would like to look at this one with x cubed and tangent inverse. 21. You want that?
Yeah, I think that's a good one to look at.
Okay. So 21. Let me copy it. And what was it? So I can put this away. So x to the third minus equals tangent inverse x. Okay. Good. So again, if you remember, arctangent is a function that is defined everywhere. Not a problem. So arc tangent x. So when I create this, I know that the function is x to the third minus tangent inverse. And number 2, I will say that f is continuous everywhere for the same reason as a sum difference of continuous functions. In step number 3, I will put the function in the calculator because I need that interval. I don't know where to start. So x cubed and then minus arctangent is right here, x, and close the parenthesis and go to second and table. So obviously they're extremely large numbers, so I have to go to the negative side. So let's say -2, let's say -1, let's say 0. The 0 is 0, so that's one solution. I can look for that. There is nothing I can do with this. So then 1, and then 2. Well, if that's the only solution, I'm in trouble, because I can use Newton's method. If that's the only solution, let me graph this for a second. So what do they want us to do? If 0 is the only solution, I'm done. Okay, so I want to graph. Oh, I see what happens is there is more than one. Okay, so I just wanted to change the viewing window for a second. Okay, so it does have 0, it has negative, close to -1, and it appears to be 1 and -1. So let me go back to the table. So negative and 0, and still negative, and then 0 and 1, between 0 and 1 and 2, and it goes already. Did I write it? Everything was okay. It was x cubed minus, yes, tangent inverse x. That's what we had, yeah. I'm checking. So
it changes between -1 and -1/2. And then
yeah, that's what I was thinking to put in, because from the graph. So -0.5. Yeah. Very good. Tricky, huh? So -0.5 and -1. So f of -0.5 is positive, and f of -1 is negative. Okay. Thank you so much. Yes?
You pick those numbers because you're looking where the interval changes from, in this case, negative to positive.
Yes. Because the function is continuous. Let me refresh your memory on the intermediate value theorem. So if a function is continuous and it's negative here and it's positive here, it has to go through the it has to have a 0. It has to have an x-intercept between this and this. So that's what we say here, that the function at -0.5, the function at -0.5 is positive, and then -1 is negative. So it must cross between -1 and -0.5, because it's continuous, and it changes sign from negative to positive. So therefore, we are going to, in step number 4, we are going to find the derivative, and that is 3x squared. And remember, the tangent, arctangent prime is 1 over 1 plus x squared. So now in number 5, I just want to make sure that when I plug in -1, because I like to start, it doesn't matter, I can start here or here. But -1 is good because the denominator is never 0, and that's okay for now. So this will be 1/2, and this is, I have to make sure that this is not 0. So f of -1 is 3 minus 1/2, which is not 0. That's all I care about. So then we'll start with x0 -1, and then we want newtons. Is x minus the function x cubed minus tangent inverse over this. Careful how we put it in. 3x squared minus 1 over 1 plus x squared. And now we plug it in. In y equals, I'm sorry, in y equals, do not delete what you have because we still have to put it in again. So just insert x minus and left parenthesis, go all the way, close the parenthesis, and divide in parentheses by 3x squared and minus 1 divided by parentheses mandatory for the denominator, 1 plus x squared, unless you have a super sophisticated, and then outside close the parenthesis. And now, second and quit, go to variables, y variable, choose function y1, select function y1, in parentheses, I plug in -1, and I get my first iteration. So my x1 equals -0.9141592654. And now when I go back and copy that entry, I have to overwrite -1 by the previous answer and make sure that it's all cleaned up and you don't have anything else. So press enter, and that's your x2. What happens at this point? I'm asking the calculator to put in this function this number, and then in this function this number, and then in this function the next number, because it picks up the previous answer. 9022507732, and now all I have to do is just repeat x3, and we haven't decided how many digits we want. Let's say we stick with 6, and 9020255724, and this should be the last one. And let's see, 2, 4, 6. I will not write it because they already repeated themselves. These are repeating. So I'm not interested in you finding if the equation has 3 solutions. I don't care. I only want you to show me one solution. I don't need to see all of them, because it's just going to be repeating the same process. That's all I wanted for Newton's method. Just remember, we have this available, which we did not have before.
I have one question here. It goes back to the x0 equals -1. In this case, you picked -1 because...
It was easier for me to plug in -1. You can pick -0.5.
Okay, alright, that makes sense.
It doesn't matter. However, I have to say that if -0.5 is closer to the solution than -1 is, you are going to get to the solution faster than I do. Maybe by 1 step faster, or maybe even 2 steps faster.
Okay.
So I will have a method with 4 steps, and you'll have a method with 3.
So in the previous question, number 22, it wouldn't have made a difference if we started at 1 or 2?
No. But as I said, the difference could be that we used 1 and I needed 5 steps. But if you start at 2, you may only, because you're closer. If you start at 2, see, you're closer to the real solution. So you're not going to need 5 steps. You're going to probably need 3 steps.
Okay.
So it does depend on, how fast the method converges. It depends on where you start. But this is not really the issue here. The issue here is to understand the method and get to the solution. If I get to the solution, the method converges very fast. If I get in 5 or if I get in 3 steps, I don't really care.
All right, thank you very much.
Is that okay? Is that clear?
Yes, it is.
Perfect. Okay. So what do we want to review next? What about graphing? So let me just give you the synopsis of this chapter 4. So we're going to look at critical numbers, right? That's one topic. Number 2, max-min on a closed interval. Number 3, graphing. Number 4, L'Hopital's rule. Number 5, optimization. And number 6, Newton. Newton's method. But graphic includes a lot. Includes the first derivative, the second derivative. It includes samples of different graphs with different information given to us. It includes slant asymptotes. It includes holes in graphs. This is a major topic. L'Hopital's rule includes, again, a lot of topics because it has 7 indeterminate rules. Indeterminate cases, basically 6, but I'm going to say 7. Optimization, we had a lot of examples. We can continue with those. Here we had 3 or 4, or just, I think, 3, Newton's method. How would you like to continue? Would you like to look at WebAssign and tell me what you would like me to help you with so you can get started on the homework in WebAssign from any section? Would you like me to choose, or